Okay, so I hope I'm audible. So good afternoon and welcome back to the week 8 discussions on mechanics and control of robotic manipulators. So I'm Isaac John. I was the TA for the entirety of the course that was handling the weekly live discussions. So as we are concluding the course on mechanics and mechanics and control of robotic manipulators. With this week, it's more or less like a continuation of what we have already discussed in uh, week 7, because in week 7 we were discussing more or less the theories behind the development of various kinds of motion controllers. And we have seen both open and closed loop examples of kinematic and dynamic controls. And for this week, we have saved one special topic on cascaded controls. Then we have also seen how can we apply the principles on kinematics and dynamics on a mobile robot actually. So just the same principles, how you can assign the frames uh, uh, as per the DH convention, then how to propagate the velocities and accelerations in the forward direction, then how to propagate the forces and the moments in the along the opposite direction, from end effector to the base. So that was about the mobile robots. So since it was more or less, uh, it more or less applies the same principles that we have already been seen. Uh, Maybe we probably won't have to discuss about mobile robots, but this week we'll mostly discuss on cascaded control. So yeah, just to give a brief overview of the syllabus that we have discussed, it was mostly simulation, I suppose, mostly MATLAB simulations of whatever we have seen during the last lectures. The standalone factor was this cascaded control and its development. Then we have also seen simulations, actually, MATLAB simulations of various dynamic control schemes. And then we have seen the kinematic and dynamic models of mobile robots using EH approach. Okay, so here, just to give a brief idea, in case of a mobile robot, you probably don't have physical joints and physical links. So what we have in effect is just a mobile base, which has 3 degrees of freedom, one along x-axis, one along y-axis, and one rotation above the vertical z-axis. So just 3 degrees of freedom. So the way we assign this DS parameters is that we'll assume, or we'll always have a global fixed reference frame. We call this inertial frame, xi and yi. And on the robot, we have a frame, fixed on the robot. We call this as body frame, xb and yb. And the 3 degrees of freedom, one translation along x-axis, one translation along y-axis, and one rotation about z-axis. We consider each of these degrees of freedom as, virtual joints, joints which are connected by massless links. And, and each of these massless links will have 1 degrees of freedom, 2 translations and 1 rotation. And after that, if you can directly apply the frames as per this DS convention, then propagate the velocities from the initial frames to the body frame. In the forward direction, you can propagate the velocities and accelerations. And then after that, you can propagate the forces and moments in the opposite direction, from the base frame to the inertial frame. And once you apply all the transformations, the propagation of velocities and accelerations and the forces, etc., you will be able to obtain, the torque needed for this mobile robot to move along x-axis, y-axis, and the vertical z-axis rotation. Okay, so now we move on to this cascaded control system. So generally, any linear ordinary differential equation can be expressed as multiple first order linear equations like this. So an input affine form is a system of this following form where x1 and x2 you can consider it to be the states. Okay, I've got a question already. When x and y translations are given, is it not rotation is defined? Why do we need to give the third d of as rotation? Because a mobile robot can it can have 3 degrees of freedom. So you will have to specify its position as well as its orientation, right? For example, an x and y position will not be enough. It with this x and y position, it can be oriented anyhow it wants, like this, like this, like this. So if you want to solve this inverse kinematics problem, you have to give the position of the frame x and y, and also the orientation of the frame, with respect to this inertial frame of reference. So I've shown in this example, I've shown both of them to be parallel, but in reality, it could be, anyhow, it could be oriented, in any possible way. So if the inverse kinematics is the priority, you will probably require, 3 variables. One joint variable along x translation, one joint variable along y translation, and one joint variable along, z axis rotation. Okay, so yeah, any system can be decomposed as several first order linear differential equations, and these x1 and x2 can be considered as a state of a system, and these particles they mostly are denoted as a system vector. The standard form is x dot is ax plus bu, a standard state space form where A is basically what we call as a system matrix, and x is actually the state vector, and x dot is the derivative of the state vector. And this small vector over here, u, is called the control input. So depending upon how these vectors are, these x dot vectors are, we can actually see how the system is going to behave basically. So for example, if there is an equilibrium for the system, maybe at a point x1e, y1e, so with the help of this vector, we can actually see whether the equilibrium is a stable equilibrium, so whether as time goes by, the system, eventually converges into this equilibrium, or it diverges away from this equilibrium, or, it does something else. You can actually ensure that with the help of this uh, uh, derivative of the state vector actually. So and general input affine form is of this form. The control input to the first system is actually the state vector of the second system. So it goes on something like this. Like for a general system, it will go something like this. x1 dot is f1 of x1 plus g1 of x1 x2, and for second system, x2 dot would be f2 of x1 x2 plus g2 of x1 x2 x3, then x3 dot becomes f3 of x1 x2 x3 plus g3 of x1 x2 x3 x4, so on and so forth. And yeah, so to manipulate or to modulate, or if you want to control the system, or if you want the system to have a forced equilibrium, it appears that you can control this input vector, whatever the coefficients of this G2, you can consider it to be the input to the first system. But theoretically, if these two systems are completely independent of each other, you can use this x2 control this x1 dot. If you want the system to be stable, you can have this x1 dot to be some negative quantity so that it will be more or less stable. You can have something like that. And to control this x2 dot, this x2 state, you can control this control vector u if both of these systems were independent. But in a robotic system, that is not the case. Both of them are coupled. So you cannot directly use X2 as a control input, or to manipulate this system, because X2 is also a state vector of the second subsystem. So you cannot use X2 as a control vector. So for that, you will have to use something that is what we would be coming across in the following slides. In robotics, or in a robotic system, uh, we have two systems. We have two levels. One is the kinematic level. Mu dot is J of Q multiplied by Q dot. And this is supposed to be Q dot, Q double dot from dynamics. Q double dot is M of Q inverse tau minus N of QQ. This is a general equations from dynamics, and this is a general equation of kinematics. And as you can see here, x1 is mu, and x2 is q dot, and x2 dot is q double dot. That is how this is going to work. And if you compare each of these terms from this system and this system, you will be able to compare. So in this equation, this f1 is 0, g of x1 is basically this term, and x2 would be this term, similar, so on and so forth. And the control input here, given here, u, would be this torque vector tau. That is what we would be supplying as inputs to the robot's joint. So moving on, what we would usually desire is that we have two subsystems defined by f1 of x1 plus g1 of x1 multiplied by x2. This is x1 dot, and x2 dot would be f2 x1 x2 plus g2 of x1 comma x2 multiplied by u. So just like what we have seen in the previous lectures, we want both of these systems to be asymptotically stable. Or in other words, as this error, for example, if x1 is the actual variable and x1 desired is the desired quantity that we want to achieve. For example, if in our case x1 is mu and x1 desired is mu desired. So if you want our system to converge towards this mu desired, we want our errors to tend to 0, right? So as x1 tend to x1 desired, error quantity tend to 0. So for asymptotic stability, we want our system to behave in a way that as time tend to infinity, this error should tend to 0, right? And for that to happen, we want our system to behave as per this differential equation, or we are trying to force our system to behave as per this differential equation. Because if you solve this homogeneous equation, the homogeneous equations for this differential equation would look something like this. E1 would be C1 e raised to minus K1t. This is how the homogeneous solution of this equation would look like. And it is pretty evident that as time tend to infinity, this error should tend to 0. And similar thing for the second subsystem. The second subsystem x2 dot equals f2 plus g2u. Second subsystem should also be asymptotically stable, or in a sense, we want our system to behave as per this differential equation, this first order differential equation. So the homogeneous solution of this would look like E2 would be some constant C2 e raised to minus K2 multiplied by t. So in this case also, it is pretty evident that as t time tend to infinity, this error term will also tend to 0. It's also pretty evident. So we'll consider or we'll analyze these two subsystems one by one. So from this equation, I can rearrange this equation like this, right? So we basically know that this E1 is x1 desired minus x1. So E1 dot would be x1 desired dot minus x1, right? So while doing that, you will get something like x1 desired dot minus x1 plus this term plus k1 E1. This will be 0, right? So, but what is this x1? This is very similar to what we have done in the, or exactly what we have done in the previous lecture. So I substitute this, sorry. So in place of this x1 dot, I'll substitute this subsystem over here. So what should I get? X1 desired dot minus f1 of x1 minus g1 of x1 multiplied by x2 plus k1 e1. This should be equal to 0. So in that case, what will be x2? Because apparently this x2 should be a control input sort of a thing. This is what we can, control so that the first subsystem will be forced to behave like this. It'll be forced to behave as per this first order dynamics. So to find x2 or to find this control input x2, you simply have to rearrange this equation, right? If you rearrange that equation, you will get x2 as x1 desired dot plus k1 e1 minus f1 of x1, the whole multiplied by g1 x1 inverse. This would be your x2. Just write it over here. Like this. So the brief summary is that, so in this first subsystem, if we can somehow control x2 such that x2 is this term, g1 of x1 inverse, k1 e1 plus x1 desired dot minus f1 of x1. If we are able to control x2 in this manner, we will be able to force the first system to behave as per this first order aerodynamics. So that essentially means the system can be asymptotically stable. And but then the question should be, can we really have x2 like this? Is it possible for us to have x2 like this? That is not exactly possible because if you can take a look at here, x2, despite being sort of an input for the first subsystem, this is also a state vector, or it's also a state for the second system, right? So whatever dynamics that plays out from the second subsystem, that can only be, substitute back onto the first subsystem. It necessarily need not be as per this law. So what can you do? Because x2 can only be played by this dynamics, not as per our wish, not as per how we want x2 to be. So just for the time being, what I'll do is I'll just call this term, or I'll just label this term as x2 desired. And with the second subsystem, what I do is that I'll try to force the state of the second subsystem, x2. So if you consider this to be x2 actual, I'll try to force this x2 into this x2 desired using this control input U. That is what we are trying to do. So to make the first subsystem asymptotically stable, we want x2 to be x2 desired, but we cannot have it like that straightforwardly because x2 is also the state vector of the second subsystem. So what we do is that we use this control input of the second subsystem to make this actual x2 tend to x2 desired, right? So if x2 tend to x2 desired, you can pretty much guarantee that E1 also asymptotically tend to 0. So now the objective would be to make this x2 tend to x2 desired using this control input U. So that is what this second error dynamics basically implies, right? So here E2 essentially means x2 desired minus x2. And here this x2 desired is actually this term, right? And x2 would be, if you go back, if you compare the robot dynamics equation, x2 would be this vector q dot. So you would try to force this q dot, you would try to force this q dot to be this term using this control input u. And from the context of a robotic system, u is nothing but the torque that we can actually give as an input. Okay, so I hope that much is clear. So then how do we do that? So if x2, so I'll rewrite the second order aerodynamics over here. E2 dot plus K2 E2, this should be equal to 0. I'll maybe label, it's already labeled. I'll simply label that or keep it aside like this. So then E2 dot would be x2 desired dot minus x2. Then I'll rewrite the second term, K2 E2. This will be equal to 0. And if I substitute this x2, if I substitute in place of this x2, the second subsystem, the dynamics of second subsystem, x2 dot is f2 of x1 x2 plus g2 of x1 x2 multiplied by u. This should be a dot. What can I get? x2 desired dot minus f2 of x1 comma x2 minus g2 of x1 comma x2 multiplied by u plus k2 e2 would be equal to 0. So from here, what can you say about u? So this u should be equal to, how can you write x2 desired dot plus k2 e2 minus f2 x1 comma x2 the whole multiplied by g2, or I'll just move this aside, whole multiplied by g2 of x1 comma x2 inverse. So I label this as equation 8. So what does this physically mean? So if you select your control input torque as per this equation, if this is your control input, you can pretty much guarantee that the second subsystem follows this error dynamics, right? So if the second system is forced to follow this error dynamics, so that basically means this x2 desired tend to x2, where x2 desired is this term, So if x2 decide is this term, that also means that this system will also be, we can also enforce that the first order aerodynamics will also be taken care of. Because if this is the control input for the first subsystem, as we have seen earlier, we can also ensure that, the first subsystem will also follow this aerodynamics. So that's why we call this as a cascaded control method, because, by ensuring that, this aerodynamics is being followed, and using the state vector of this, we'll, backtrack into this system, which would again make it sure that the first aerodynamics is also followed. So in that way, both the systems will, tend to be asymptotically stable using that. So there is also one more thing. We also need to verify that whatever that we are trying to do is stable everywhere. So for that, maybe if you can recall from the lecture, there is something called this, Lyapunov. I think it's called Lyapunov's direct method. So what it says is that, like, you can have a candidate function. Maybe we call this as a function v. It can be any function. Maybe I can have this function as, E1 transpose E1 plus half E2 transpose E2. So the criteria of selecting this function is that it should be positive definite everywhere. Like v of E1 comma E2 should be, greater than 0 for all E1 comma E2 not equal to 0. And what this Lyapunov's direct method says is that if you can find a function like this, which is positive definite everywhere. So this is just like, like a parabolic equation, which is irrespective of whether E1 is positive or negative, or E2 is positive or negative, irrespective of the case, this function, this scalar function v, is always going to be strictly positive. And if you can somehow if you know that the derivative of this function, E1 of v dot of E1 comma E2 is less than or equal to 0 everywhere, maybe probably for all E1, E2 not equal to 0, then the Lyapunov method states that the system is actually asymptotically stable. So the converse is not necessarily true. If you cannot find a function like this and ensure that its derivative is less than 0, it does not really mean that the system is not stable. But if you can somehow find a function like this, and and if its derivative is less than or equal to 0, that basically means that the system is always going to be stable. You can also consider it to be, this function to be an equivalent of, you can consider it to be an energy equivalent function. Maybe, a kinetic energy of a system is proportional to its, its velocity square. So a similar thing, and this term is basically a square of the first error, and this is basically the square of the second error of the second state. So what this term basically means that the error is basically dissipative. So as time evolves, if v dot is less than 0, this term v would gradually loses its value, and ultimately it'll basically settle to its equilibrium point. So in this case, the equilibrium point is E1, E2 is 0, 0. So like as time evolves, if v dot is less than 0, as time evolves, the function v of E1, E2 would spiral down all the way to 0. And there are a lot of ways, theoretically, you can select this Lyapunov function This is actually a pretty valid Lyapunov function because uh, as per the as per the criteria, you only need to ensure that the function is positive definite, irrespective whether E1 is greater than 0 or E2 is greater than 0. And if you can somehow prove that V dot of E1 comma E2 is less than 0, or you can choose your control input in a way such that V dot of E1 comma E2 is, is going to be less than 0, then that itself is actually a good proof that the system is more or less stable, asymptotically stable. So then what are this E1 and E1 dot? So if I take the derivative, V dot of E1 comma E2, this will be, if I take the derivative, it will be E1 transpose E1 dot plus E2 transpose E2 dot. I'll label this as probably equation 9. So then our objective is to find out what are these terms E1 dot and E2 dot, and whether this term is going to be less than 0. That is what we are now trying to prove. It's more or less like a proof, actually. Like if you can somehow prove, then if you can somehow prove that this is going to be less than 0, that essentially means that your system is always going to be stable. So while designing a control system, this is always going to be a criteria, because in order to ensure that your designed control system is always going to be stable, you need to prove your stability using this Lyapunov direct method. So if you cannot prove, it does not mean that the system is unstable. You will have to use some other methods to investigate for the stability of the system. But if you are able to find a function like this, a positive definite function, and if you are able to prove that the derivative is always going to be less than 0, then that guarantees that your system is always going to be stable. So how do we find out each of these terms? So this E1 is basically the difference between the decide state and the actual state of the first subsystem. So I'll label this as equation 10. So then what would be this E1 dot? E1 dot would be x1 decide minus x1 decide dot minus x2 dot. And we'll leave that aside. And what is this x2? So x2 again is, sorry. And from this equation, E2 as E2 is the difference between the decide state and the actual state, x2 decide minus x2. For I label this as equation 11, I label this as equation 12. And from here, what would be x2 actually? So x2 would be x2 decide minus E2. I label this as equation 30. Okay, so we'll now go back to this equation 11. So what can we do? I think, I think I've made a mistake. This is supposed to be x1 decide. Right? E1 dot is x1 decide minus x1. So in place of this x1 dot, I'll write the dynamics of the first subsystem, f1 of x1 plus g1 of x1 plus x2. So E1 dot would be, so I'll write it like this. From 11, E1 dot would be x1 decide dot minus f1 of x1 plus g1 of x1 multiplied by x2 So in place of this x2, I can write this term over here, right? So if I write it like this would basically mean x1 desired dot minus f1 of x1 plus g1 of x1 multiplied by x2 desired minus e2. I hope I'm correct so far. And in place of this x2 desired, we have already found it to be this term, right? It is only when this term is, x2 desired is this, then only we'll be able to, follow this first order aerodynamics system. So instead of this x2 desired, I'll bring it forward. So I'll carry it forward to the next page. E1 dot would be x1 desired dot minus f1 of x1 plus g1 of x1. So I'll open this curly bracket and I'll substitute this term in place of x2 desired. So that makes it g1 of x1 inverse. I'll just open the curly bracket, k1 e1 minus, or is it x plus x1 desired dot minus f1 of x1. Then we'll have this e2, I suppose. Close this curly bracket, close this one. Yes. So that is what this term is. E1 dot is this much. So if I further simplify, so I'll further simplify this equation. E1 dot is, so here you can see there is a positive x1 desired dot, and this g1 and g1 inverse will get cancelled. And there is also a positive x1 desired over here, but there is a minus outside here. So this term and this term will get cancelled. So I'll just cancel those two terms. And there is also a minus f of x1 term here. And there is also a plus f of x1 term here, because this minus and this minus become plus. And this g of x1 and g of x1 inverse will get cancelled. So these two terms will also get cancelled. So what we have remaining over here would be this term, and with this minus, that'll be minus k1 e1. Then we have this term over here, multiplied by this g1 x1. So this will be minus g1 of x1 multiplied by e2. So far, from this equation, we have found out E1 dot. Now our objective is to find out E2 dot. So the thing is, the objective is to prove that once we have determined E1 dot and E2 dot, this term V dot E1 E2 should be less than 0. So since we have this control input on our hand, since we have that as, we can basically choose it as per our requirement. We can choose this control input u in a way that this term along with this term would make this v dot less than 0, right? So I'll show an example. So if this E2 dot is, so I'll write it over here. If E2 dot is something like, I don't know, how do I write it like that? Yeah, if I select E2 dot in a way that minus K2 E2 minus G1 of X1 E1. So which equation is this? I'll label this as equation probably 13. So if E2 dot turns out to be like this, there's a big if over here. So I'll just label this if. So what I mean is that if E2 dot is as per this term and E1 dot is as per this term, so what happens if you substitute this E2 dot onto this equation, onto this V dot? So we'll just see what is going to happen. So V dot would be E1 transpose, E1 dot would be this term. So I'll write it like that. Minus K1 E1 minus G1 X1 E2 plus the second term, E2 transpose E2 dot. So E2 transpose. So E2 dot, if E2 dot turns out to be like this, how can I write it? E2 dot would be minus K2 E2 minus G1 of X1 E1. Okay, so yeah, one thing, yeah, if E2 dot can be like this, now instead of minus, if there is a plus like this, so this becomes a plus. So what happens if you expand this term? If you expand this term out, you will have minus E1 transpose K1 E1 minus E1 transpose G1 of X1 E2 minus E2 transpose K2 E2. Then you will have plus E2 transpose G of X1 E1. So basically, you will end up with these two terms, this term and this term. So it will become minus E1 transpose K1 E1 minus E2 transpose K2 E2. And these two terms will get cancelled out. This term and this term will get cancelled out. So this becomes your V dot E1 E2. So it's guaranteed that this term is always going to be less than 0, irrespective of what is your E1, whether it is positive or whether it is negative, or E2, whether it is positive or whether it is negative. This term V2 dot of E1, E2 is always going to be 0. So, that is a good assumption, and the reason I call this as an assumption is that it's more or less like a trial and error process. There is no singular method to follow. You can even choose this Lyapunov method, this Lyapunov candidate function to be something else. But as long as you follow the rule book, you can ensure that the system is going to be asymptotically stable. And the same thing here, E2 dot need not be something like this. It can be anything. It can be something else. But as long as you can ensure that V dot is always going to be less than 0, your choice of E2 dot, whether it is, even if it is something else, it's always going to be fine. No problems at all. It does not have to be this one. And the reason I said I can choose it this way is because I know the solution prior hand. I know this beforehand through trial and error process. That's how we usually do this. And there are also some systematic methods to obtain this Lyapunov candidate method, but it's not always a singular solution. There are always multiple possible methods to come up with this. So yeah, V dot is always going to be less than 0, so that asymptotic stability is always going to be ensured. Our assumption, if E2 dot is as per equation 13, that assumption is going to be valid. It's properly valid. But then how can we make sure that E2, how can we make sure that E2 can be forced to this term? How can we make sure that? So we can ensure that E2 becomes this term by forcing the second order subsystem using the control input U. So the way that we use is that we have to use the second control input in a way to force E2 dot to be like so. So yeah. So how do we do that? How do we select the control input? So I'll erase this term, and we'll now look at the decide or the required the required control input. So yeah, how do we do that? Okay, so so x2 decide dot. Yeah, so our second subsystem x2 E2 should be as per this. E2 would be x2 decide dot minus x2. This was our second subsystem. I'll label this as equation 14. This is the second order aerodynamics. And in place of this x2, I can bring back the second order dynamics of the system. That'll be E2 would be x2 decide dot minus f2 of x2. Sorry, this will be E2 dot, I suppose, right? Yeah, so f2 of x2, sorry, it'll be x1 x2 plus g2 of x1 comma x2 multiplied by u. And this is how we want E2 dot to be. It should be something like this. So if we want E2 dot to be like this, how can we select this U? That is our question. So how do we select this U? So yeah, so through some manipulations, E2 dot could be written as x2 decide dot minus f2 of x1 comma x2 plus g2 of x1 comma x2. So in place of u, what I'm going to write is, in place of u, I can write it like this: g2 of x1 comma x2 inverse. So both of these terms will get cancelled. So I don't want this term here because this term f2 term does not appear here. So I'll write a minus f1 x1 x2. So I'll write it here minus f2 x1 comma x2. Then I also don't want this term, right? So if I don't want this term, because this x2 decide dot does not appear in this equation, so I'll write a plus x2 decide dot over here. So then what else? What are the other terms that we don't really want? Then we have these two terms. These terms is what we require. These two terms is what we require. So I'll add those two terms over here plus K2E2. If I add that term, then I'll also add this term, I suppose, minus G1 x1 comma E1. So this curly bracket will be here, and this negative sign will also be there. So yeah, this entire term over here, that will be your control input U. So the U is going to be G2 of x1 comma x2 inverse minus F2 x1 comma x2 plus x2 desired dot plus K2 E2 minus G1 of x1 E1. Unless I am very much wrong, because that will be our control input for this cascaded control. So once you have derived this, you can substitute the corresponding values. If you compare our robotic system, eta dot is J of Q multiplied by Q dot, and Q double dot is M of Q inverse tau minus N of Q dot. So instead of all those things, G2, F2, G1, all these terms, you can actually substitute the corresponding terms. And for this x2 desired dot, you already have this x2 over here in this equation. And this two, x2 desired. If you take the derivative of this equation, you will be able to get x2 desired dot. So yeah, once you have that, you will be able to obtain the control input, which is nothing but this one, torque, so that you can supply onto the system. So this is how your control input should be, so that your both of the systems will be asymptotically stable. So yeah, that is about this cascaded control, because probably in the lectures there may be some some small mathematical errors. I think here we have done it probably correctly, without any errors. But I suppose the logic is, even though it's a bit trickier to understand, I suppose it has a lot of going back and forth, because it's not derived in a linear fashion. We'll have to, at some point we'll have to travel a bit further forward. We assume that E2 has to be something like this, then we'll come back, and that is how when we derive this control input Q. But with this, you can basically ensure that E2, the second order aerodynamics is followed, which in turn will force the system to follow this first order aerodynamics. So that's why it got its name cascading. The second system basically forces x2 to become x2 desired. That becomes the control input for the first system, and that makes the first system to converge asymptotically. Yeah, that was about this asymptotic stability of this cascaded control. And the remaining topics for this session were all, it more or less overlaps with what we have discussed in the previous week. What we have discussed, the kinematic and dynamic controls, both open and closed loop examples. And the remaining part would be, the kinematic and dynamic simulation of mobile robots. So with that, we'll solve some sample questions. Again, you may find a lot of overlap with what we have seen in the previous section. So the only highlight was the discussion of this cascaded control. Okay, so the first question is, this inverse dynamics control would still track the desired trajectory even if the following conditions are not satisfied. Even if the following conditions are not satisfied, if it are not satisfied, is it true or false? Okay, so we got an answer. It says it to be false because the general dynamic equations of motion is tau is nothing but m of q multiplied by q double dot plus n of q dot. And this inverse dynamics control simply asks you to throw your desired trajectory. If you have this desired trajectory defined by the velocities, so the positions, eta desired or q desired, q desired dot, and q desired double dot, you are simply throwing this into this dynamics equation. So you will get torque as m of q desired double dot plus n of q desired dot, right? And this method would fail if q desired double dot is 0 and if the initial conditions, q actual, q of 0 and the desired initial positions and the actual position is not equal, and the actual velocities, initial actual velocity and the initial desired velocities are not equal to 0. So the criteria for this method to fail would be this. So there is an or actually, or ID fails. So if either of these conditions are not satisfied, inverse dynamics basically fails. So in that regard, the correct answer is indeed false. It will not track if these conditions are not satisfied. So yeah, the answer is indeed correct. It's indeed false. So I agree with that. Okay, so now moving on to question 2, a motion-based or model-free control are easy to use but sluggish and produce poor tracking performance. So a motion-based or model-free, a motion-based control, something like a PID control, which probably does not have any terms from the model. It says that they are easy to use. Yeah, obviously they are easy to use because if you have some sensors, you can make use of this data from the sensors, and you essentially can have this PID control as AP multiplied by this error term, AP multiplied by E tilde plus KD multiplied by the derivative of this error plus KI multiplied by integral of this error. You can supply this to be your control input, or you can supply it to be your velocity input. Either case, it'll be as simple as this. You don't need to have a dynamic model or anything like that. So in that regard, it is easy to use, but there is always a sluggishness associated with these sort of controls. So just like I was mentioning, like if a system has more inertia along one direction and it has less inertia along another direction, and since the control law does not exploit that factor, when the system tries to move along a direction with higher inertia, it'll be very slow, it'll be very sluggish than when it compared to move along a direction that has lower inertia. So like if the system, if we can have some information about the model, if we can have some information about the model, we can scale this control input when the system is trying to move in a direction that has more inertia. We can scale the control input, we can multiply it and apply them when it is trying to move in a more difficult direction. But if the system is model free, it has no information about the model, and we cannot make use of this information, that the system is more, sluggish in one direction, or more, it has more inertia along one direction. We cannot use that. So that makes the system very sluggish. And it can also, due to that, it can also produce some poor tracking effect, due to its sluggishness, or due to its uh, non-adaptive nature, it probably, causes some poor tracking performance, which may lead to some overshoots, For example, if this is our desired state and the system has poor tracking performance, it probably may overshoot. And when it tries to correct, it will overcorrect. And again, it will try to overcorrect. It goes on like that. So that produces some sluggishness, and it also produces some poor tracking performance. So that statement is indeed true, I believe. Unless there is any conflict of motion, suppose that is indeed true. Yeah, it is indeed true. Okay, now moving on, question 3. For aerial mobile robots and underwater vehicles, the degree of freedom is it 1, 2, 3 out of 1 to 6? What would be the degree of freedom for aerial mobile robots and underwater vehicles? Yeah, I got an answer as 6. That is indeed true, because aerial drones, they can move along 3 directions, X, Y, Z, and they can also rotate along 3 directions. We call them as roll, pitch, and yaw. Rotations about either of these 3 axes. And the same in case of an underwater vehicle. An underwater vehicle can also move in 3 directions, X, Y, and Z, and it can also, realize all 3 orientations. But there are some special cases. What about land-based mobile robot? If the robot is land-based, if it purely moves on land, then it can only have 3 degrees of freedom, right? It can only have 2 translations along X and Y, in case of just like in the case of a mobile robot, and 1 rotation. So that makes it 3 degrees of freedom. And there is a class of underwater vehicles. It's not necessarily underwater. We call them water surface vehicles. It will not go underwater. So again, that will also have 3 degrees of freedom, 2 translations and 1 rotation. So that is also one more case where, water surface vehicles and, a land-based robot, that those will have 3 degrees of freedom. But aerial mobile robots and underwater vehicles, they will have 6 degrees of freedom. So yeah, that is indeed the correct answer. 6 degrees of freedom. Okay, so now moving on to question 4. It's a true or false system. In order to eliminate steady state error, a modified control law is sometimes used. The modification involves addition of a derivative term to the control law. So is that true or false? Because typically when we want to eliminate this steady state error, we use this integral term. So whatever error that is accumulated over time due to this small, steady state error between the true value and this actual value, you will integrate this error from time t equal to 0 all the way to the current time, and you add the cumulative error as a control input. But in case of this derivative error, it depends on the rate of change of error. So if the error is slowing down, the derivative term will also decrease, or if the error is shooting up, or if it is increasing up, the derivative term will also, it'll also increase. So yeah, steady state error is always going to be associated with the integral term, not the derivative term. So in that regard, this answer is also false. Okay, so moving on to question 5. The second order error dynamics is stable as per the following condition. So as per which of this following uh, options does does the second order aerodynamics becomes stable? So the second order aerodynamics is q1 decide double dot plus lambda 1 q1 tilde dot plus lambda 2 q2 tilde. This should be 0, right? And the homogeneous solution would be q1 of t would be c1 e raised to minus lambda 1 t plus c2 e raised to minus lambda 2 t. And this is only possible, this solution is only possible only when lambda 1 and lambda 2 are greater than 0. So if lambda 1 and lambda 2 are less than 0, these terms becomes positive. So as time grows, these terms will grow exponentially. But if lambda 1 and lambda 2 are positive, this will become negative lambda t. So as time goes, both of these terms would decrease like so. So C and D are the same. That is what I've got as this answer. No, I don't think so, because C says lambda 1 and lambda 2 are greater than 0, and D says lambda 1 is greater than 0 and lambda 2 is less than 0. Yes, exactly. So I think C is indeed the answer actually. Yes, C is the answer. Okay, now moving on to question 6. From the following options, identify the correct situations to be satisfied so that the inverse dynamics control can be satisfied. I think we have seen this earlier. So for inverse dynamics to be satisfied, Q decide cannot be 0. So this should be satisfied. And the initial velocities, the initial actual velocity and initial desired velocities should be equal. So this equation should be equal. And initial desired position and initial actual position should also be equal. So I suppose this is true, and these two are also true for inverse dynamics to be able to work. So I reckon option A and option B and E are wrong. Check the answer. Yeah, isn't it true? And moving on to question 7. It's a lengthy question. It says, in order to satisfy the objectives, there are the following objectives actually. As time tend to infinity, mu tilde tend to 0 and mu tilde dot tend to 0, where mu tilde is mu desired minus mu, and mu tilde dot is mu desired dot minus mu dot. A control law on task space can be devised because these variables mu are all defined in task space. Mu, they are all defined in task space. Okay, because that makes sense, because as an operator, it's much more convenient to uh, lay down these objectives in task space, because then we'll be able to know how the tip of our end effector would be moving. We can actually visualize that, but we cannot, it's not very easy to, define these objectives from joint space, because to move the center effector from one point to another, we cannot really visualize how the joint space is going to look like. It's much more intuitive to visualize how the task space, would be moving. So the following control law can be decided. This actuation force F in task space is m of mu. This is the mass matrix in task space multiplied by mu decide dot plus lambda 1 mu tilde dot plus lambda 2 mu tilde plus n of mu dot mu. This is the vector of Coriolis and centrifugal effects. And this is basically the computed control law in task space. So where m of mu, n of mu, and f are the mass matrix, vector of Coriolis, and the centrifugal effects, and the force vector in actuator spaces. However, the control inputs are to be given to the actuators despite the control law is defined in task space. So control law is defined in task space because mu dot, and mu double dot are more easier to be defined in task space. So find from the below options the correct control inputs to be provided to the actuators. So use the following hints to convert the mass matrix and Coriolis vector to joint space. So you have to find out, like, if this is the computed control law in task space, what would be the computed control law in joint space? So it could be a tricky question. So you can use these following hints to go to this following control laws. How can one do that? So the left-hand side m of mu is the mass matrix in task space, and m of q is the mass matrix in joint space. N of mu is the Coriolis vector in task space, and these are the Coriolis vector in joint space. So what can we do that? So we'll try one approach. We can try and substitute we can try and substitute these terms into this equation and see where it will take us actually. So yeah. So I'll write this computer control law. F would be m of mu decide double dot plus gamma 1 mu tilde dot plus gamma 2 mu tilde plus n of mu dot mu. Okay, so if I write something like this, so instead of this m of mu, if I substitute this equation, what will I get? So I'll get it as J inverse transpose M J inverse mu decide double dot plus gamma 1 mu tilde dot plus gamma 2 mu tilde plus, instead of this n of mu, I'll substitute this term over here. So that makes it J inverse transpose N minus M mu j dot q dot. And again, we have an mu over here. So instead of this mu, I'll have to substitute again this term. So that makes it, so this term will become minus J inverse transpose M J inverse J dot Q dot. So I'll just substitute this term over here. So, so now what can we do? So you can see that there is a J inverse M J inverse over here. We also have the same term J inverse transpose M J inverse transpose here. So I can take these two terms inside the bracket, considering this as a common factor. So if I do that, I'll get it as J inverse transpose M J inverse mu decide double dot. Then I'll get this plus gamma 1 mu tilde dot plus gamma 2 mu tilde plus that remaining term minus J dot Q dot plus J inverse transpose M. I suppose I am correct until now. This would be equal to this F. This F over here. And from this robot statics, we know that this F or this torque is related to F as J transpose F. It's you can derive this equation from conservation of power. I believe we have discussed this during week 3 or week 4. If you equate the power in task space equal to the power in joint space, you will end up with this equation. And if in place of this F, if you bring this J transpose over to this other side, so what will you get? So from here, you can get it as, we can get F as J inverse transpose, J inverse transpose tau. Inverse transpose torque. Right, so that we'll get our equation as such. So I'll directly replace this F as J inverse transpose tau over here. That'll be J inverse transpose torque. So I'll just erase this. So from both sides of this equation, I can cancel this J inverse transpose. So I'll cancel this one. I'll cancel this one. I'll cancel this one, which would leave us this torque in joint space as mass matrix in joint space multiplied by this Jacobian J inverse mu decide double dot plus gamma 1 mu tilde dot plus gamma 2 mu tilde minus J dot Q dot plus this N over here, N of Q dot, that too in joint space. So this is how our torque equation in joint space would look like if the trajectories are defined in task space. So I hope that is clear enough. because the hints are all directly provided. You only need to substitute these hints directly onto this computed torque control. And once you rearrange this using some linear algebraic manipulations, you will finally end up with this equation for this actuation torque. So I suppose our right answer is option E, I suppose. Yes, option E. Or is it option? I think it's D, I suppose. Option D. So if you check the answer, it is option D. It's indeed true. So yeah, moving on to this last question for this session. Identify the closed loop control laws from the following. So which of them are closed loop? So inverse dynamics is obviously open loop. Computed velocity is closed loop. Inverse dynamics is open loop. Computed torque control is closed loop. Cascade control is also closed loop. PID control is again closed loop. So how many closed loops do we have? We have option B as closed loop, option D as closed loop, E is also closed loop, F is also closed loop. These are all closed loop. So that is indeed our answer. Yes. So yeah, that's it from my side. My intention was to discuss mostly on this cascaded control and also a few questions. And as you can see, these are all more or less, it's more or less overlapping with the topics that we have discussed in the previous during the previous tutorial session. Yeah, so unless there are any more doubts, we can wrap this session up.
Sir, week 6 live section PPT is not uploaded, sir. Week
Week
6.
6 PPT is not uploaded, huh?
Yes, sir. Yes, sir.
Okay.
And for a
Yeah.
while, we can discuss assignment 7 solutions, sir. Please, can you open the assignment 7 solutions?
Actual assignment 7.
Yes, sir.
Okay. I'm not sure if the deadline is over or not.
Yes, sir. It is over. Just I want to some
Sure.
clarification.
Okay. I may not have the answers. Do you have that questions with you? 20. Yeah. Okay. Which question?
So many are there, sir. Like here, this like question 8, they are asking to identify the odd ones. Sir.
Question
They are
8,
asking one
they're
question.
asking
Like
the odd.
one of the question is they are asking the odd one
So let me
by
check.
giving this list.
Let me check. What are the odd ones? Which question is that? Pick the odd one from the following: inverse dynamics control, computed velocity control, computed torque control, PD control with gravity compensation. Okay, okay. So yeah, what about the question?
Actually, I have selected cascaded control, which is not, I think, which is not discussed at that time.
Okay, but it was discussed in the. It was probably discussed in the lectures, I suppose, right?
Might be. Yes, sir, might be.
Yeah.
That means what is here inverse and inverse. These two are the OP loop, no, sir. The both.
Yes.
Can you share the question, sir?
Question
At least
13.
the sequence,
Can
the
can you see?
sequence of questions.
Can you see my screen?
The
If I write this
sequence of
question,
questions.
is it possible to see my screen? If I'm
This
writing it
is
over.
the eighth, no, sorry. This is This is somewhat, it is not assignment 7, sir. I am asking to show me the assignment 7.
Yeah, that is what I'm writing over here. Can you see my board? Can you see my?
Yeah, yes, sir, yes, sir.
Okay, so inverse dynamics. Then this is option A. Option B is computed velocity control. Then C is computed torque. Then option D is PD control. Then option E would be PID control. And option F is cascaded control. So what was your logic? You were saying something about inverse dynamics being open loop, right?
I am not saying any logic, sir. Just I am asking explanation. So is it
Ah,
only inverse dynamics is the odd one, sir, now?
let me check. Yeah, I suppose that is the only open loop, right? Everything else is computed velocity is closed loop, computed torque is closed loop, PD control is also closed loop because there is a feedback term coming. PID control is also closed loop. Cascaded is also a closed loop. So inverse dynamics is only the open loop. Everything else is the closed loop. So
Okay, sir.
that
Okay,
makes
sir.
it open loop.
Sir, I will try the assignment 7 and I will try to open the share the 7, sir. Try.
Okay.
Sir, whatever question we just discussed and the eighth solution, they look the
Yeah.
same, but most of the answers here, I see them as some of the answers here as open also. But the open was not given in this. Inverse dynamics control is open. Inverse differential. Oh. Okay.
Sorry, velocity inverse differential kinematics is also open. Yes.
In the answer options which you have written there, I was not seeing inverse differential kinematics in the given
Well,
answer options.
Inverse
Since
differential.
since the reasoning behind why this is an odd one out is not given, I was not supposed to use other means, but I was using meta and asking it, what is the reasoning behind this? Then it
Okay.
said
So yeah.
some of these are torque based and some of these are velocity based. And it also said the cascaded control has two loops. So this is an odd one out. So the reasoning why,
Okay.
so
So the reasoning
that
is
kind
not.
of
Okay. Okay. The reasoning is not
yeah,
provided as the answer. So only the correct answer is provided, but not the reasoning.
right. So
Yeah.
people may see it from different angles and they may get different answers for this question.
Oh, okay. Okay. But I thought this would be very easy because
If the thought process
don't-
has come to
yeah,
open loop, closed loop, definitely we would have identified it. But
yeah.
the thought process was not there. Because it
Okay.
belongs to this one, maybe you might have thought that this is people will answer it based on open close. It's
Okay.
okay,
Okay.
sir, no problem.
Okay. Maybe we can probably take this feedback for the next run of this course. But yeah, the
Okay.
feedback is very valid. Actually, the reasoning behind any of these answers are not given. It's only the correct answer that is being given. So it's the correct answer is given as inverse dynamics, but why is it inverse dynamics? That logic is actually not given. Yeah, that is true. That is maybe we can improve that. Maybe for the next upcoming runs.
Sir, shall I share the screen, sir?
Yeah, if you can please. Let me stop mine.
Okay, sir.
Okay, is it possible for you to share?
Only the host can share in this meeting.
Okay, okay, all participants, I'm enabling that. Okay. Yes. Is it now possible?
Sir, are you able to see my screen now?
Not yet. It may take a few seconds, I suppose.
Is it okay, sir?
No, it's not yet. Your screen is still not visible. No, your screen is still not visible actually. So I'll
Okay,
if I can, let me log into my account and see if I can share.
yes, sir. I will read now. Okay, I will read one point here. There is one block diagram. A basic outline of a control system is depicted in the following figure. Identify the correct components from the following.
Hmm.
I missed. Actually, I have not given any option. Can we discuss the block diagram, sir? A
Sure.
basic outline of a control system where
Yeah, we can.
plant, controller, sensor, feedback signal, and error signal are there. And they are asking what is A block and B block, C block, etc.
Okay,
Towards the beginning of the last lecture, you have shown those things.
Okay, sir.
Yes.
Can you see my screen now? My screen, is it visible?
Just checking, sir.
Okay.
Yes, sir. It's visible.
Yes, sir. Yes, sir.
Okay, so yeah, question 2. I can see. So yeah, how does what is the problem regarding that question?
Anything, not a problem, sir. Just
Yeah.
we are one more time we are discussing that, sir.
Sure, no problem. So can I go back to my notebook? Is it fine?
Yes, sir.
Okay, so let me just revert back. It's slow. Okay. Should be up anytime soon now. Yeah. So the question is something like this. We have a summing point over here like this. We have an input reference coming from this side. And over here, we have a block which is unknown. We are only being given as option A, and following this, we have another block, what we call it as B. And over here, we have this output. And from here, we have this block C, and then it will go all the way back to the summing point. And this is labeled as D, this is labeled as E. Yes. So what are the following options? We have the plant, also have
Controller.
controller, we have the sensor, then we have the feedback, then we have the error signal. So which would be the most straightforward thing to put first? Sorry. Right. So yeah, this is a typical a typical block diagram or a typical control loop of a feedback system. So yeah, the difference between output and this input, you can call this as an error signal actually, right? For example, if your room has an air condition and you want your system to be 24 degrees Celsius, but from the sensors you are getting it to be 25 degrees Celsius. The difference between your input reference and the output from the sensors, that is what we call as error signal. So option E, the difference between the input reference and what you obtain from the sensor over here. So this is, the output that is measured, the output it's actually a loop. So we cannot do this in a, we cannot start from a place and, and a place, because it's a loop. So option C becomes a sensor actually. This is actually the sensor, because we are basically measuring the output, whatever we are getting, and we are measuring using some sensors. Maybe it's a temperature, and we are actually comparing the measured temperature from the sensor, and whatever we are supplying as an input, and the difference between this input and the output from the sensor, we call them as this error signal. And the output from the sensor is nothing but the feedback signal, actually. Whatever we are getting from the output, that is the feedback. And the difference between the input reference and the feedback is the error signal. And what do we do with this error signal? We'll do some control actions, maybe it can be a PID control. We take the derivative of the, multiply by this constant gain with the derivative of this error, or we proportionally add some, a constant or a matrix to the error, or we'll, integrate all the errors to eliminate the steady state error. Whatever be the case, it could be PID, PD, or PI, or even PID. And whatever output we get from this controller, we supply that onto the plant. Maybe if the plant is an air conditioner, the command signal from the controller will be supplied onto this plant, which in turn would give you an output, which is, read by the sensors. And the sensor reading would go to the, will be compared with this input reference, which would give you this error signal, and it goes on and on and on. So I suppose the answer is option A is controller, option B is plant, option C is sensor, option D is feedback, option E is error signal. So I suppose that is the answer, I think. Controller, plant, sensor, feedback signal, error signal. I think that is, that was indeed the answer. So any more ambiguity?
Sir, please move to the assignment, sir. Now it is showing notepad now.
Yeah. Now, if you want me to move to this assignment, I shall do so. No problems. I'll share the screen. And I hope you can see my screen. The correct answer is controller, plant, sensor, feedback signal, error signal. I suppose.
Okay, sir. Then next question.
Next question. Question 3.
Just, sir, I will check.
Okay.
Sir, can you go to week number 4?
Week 4.
Assignment,
okay.
Week 4.
Yeah, assignment week 4.
There
okay. Which question?
Now? Can you scroll now? Still.
Yeah.
Still. There. That fifth question. You
Yeah.
see the rotation matrix is I with respect to I plus 1, whereas the position matrix is I plus 1 with respect to I. How do they put this and stuff? Why not they write I plus 1 R as R and say with the same notation?
Because in this case, if you take the link any link actually, it'll have two ends, right? It'll have one end. For example, if this is link I, the frame that is always going to be fixed at the link I is always going to be at this point.
Yeah,
if you consider this
your
direction
board
to
is
be the
not clear,
base.
sir. Sir, you have to go to whiteboard.
Oh, sorry. Yeah. Okay. Yeah, sorry. Okay, so if you consider this to be the direction of your base and this to be the direction of this end effector,
Okay.
a link will always have a frame attached at the end that is towards the base. We call this end as the proximal end, and we call the other end towards the end effector as the distal end. Right, and if you consider if you consider the z-axis to be vertically up, if you consider this to be a revolute joint, z-axis will always be up like this. So I'll label this as zi, and the x-axis will be along the link length. This will be xi. So and the other frame, the other frame for the other link, maybe if there is a different link here, something like this. And again, this is, if you want assume this to be connected by a revolute joint, it will have its own frame, zi plus 1, and there will be another link, xi plus 1, and this is link I plus 1. So the link length for link I, if this is link I, it is always going to be measured along xi. It's always going to be measured along xi. So if this is the link length, if you call this as P, we refer this P from I to I plus 1 with respect to I. That's why we label it as like that. I plus 1 with respect to I. And the position of this I plus 1th vector is always reference with respect to I. Because link length
then
of...
why?
Yeah.
Okay, I understand. But why not R also as I plus 1 with respect to I?
R as I plus 1 with respect to I.
Yeah, rotation.
Because rotation matrices we are actually bringing from, since it's a forward propagation, we are propagating velocities, be it angular velocities and linear velocities from ith joint to I plus 1th joint.
Okay.
Right. So ith joint to I plus 1th joint. So if you know something at the ith joint, if you want to bring it to the I plus 1 joint, you have to use this rotation matrix, I plus 1 with respect to I.
Okay.
That is why we have this rotation matrix.
Okay. Fine.
Yeah.
Sir, 12th question, sir. Assignment 7, 12th question.
Okay, assignment 7, 12th question. Assignment 7, 12th question would be, okay, if it is okay, I'll just read out and I'll write the relevant points. The controller of a robot manipulator is required to have the following second order aerodynamics. So the second order aerodynamics given in the question is q tilde double dot plus lambda 1 q tilde dot plus lambda 2 q tilde is equal to 0, where q tilde is given as the difference between the decide and the actual joint variables, and lambda 1 and lambda 2 are assumed to be greater than or equal to 0, or it's strictly greater than 0 as per the question. So if the dynamic equations of the robot are, so the dynamic equations of the robot are also given as m of q, q double dot plus n of q, q dot. So what is the control input tau c required to achieve the required aerodynamics? That is the question actually. So this is straightforward what we have discussed in the weekly session, and it is also straightforward application of the computed torque control. So yeah.
Sir, anywhere we have used tau c, sir, anywhere we have used tau c.
Tau c was just a meaning actually, just to imply that that would be the control input. That's all. We haven't used tau c in anywhere in the lectures, but it is to, in this question, it is just to signify that would be the control input that you would be supplying onto the robot, so that this will be the aerodynamics that will be followed. Because we have already used tau here, so that's why we are using this tau c as a control input. Otherwise, there will be two taus, right? Tau here and again control input tau again. We also use the same, symbol to define two terms actually, one for the dynamics and one for the control. So that is why we gave this distinction between tau and tau c.
We confused and I took the MQ inverse. Later, I thought that it is very simple one. Instead of tau, it should be tau c.
Okay, yeah. The reason was to avoid confusion actually. So I'm sorry that it caused more confusion, because we have used it for tau. We have used it to, write this dynamic equations of motion. So
Okay,
we thought
sir.
probably this tau c would be, it'll be more distinctive for this control input. So that, both of these signal symbols will be distinctive. So yeah. But I suppose, shall I derive how this answer is? We got this answer, or do you
Can
know
you
the
show,
answer
sir,
already?
tau c? Can you show tau c derivation? Or
Yeah, sure.
you are making tau as tau c, that's all?
Yeah, simply make tau as tau c, that's all. It's just to signify that will be the control input. Otherwise, it can be confusing, right? Otherwise, it can be confusing, because if this is your desired dynamics, so I'll rewrite this equation like this. So instead of q tilde double dot, I can write this as q desi double dot minus q double dot plus lambda 1 q tilde dot plus lambda 2 q tilde. This will be 0. And instead of this q double dot, I can use this equation, right? So from this equation, I'll label this as equation 1. So from 1, q double dot would be tau minus n of q dot, the whole multiplied by m of q inverse. So if I substitute this equation onto this, you will get q desi double dot minus m of q inverse tau minus n of q dot plus lambda 1 q tilde dot plus lambda 2 q tilde. This will be 0. So if I take this term, this m of q inverse tau, to the other side of this equation, you will get q desi double dot plus m of q inverse n of q dot plus lambda plus, I think, lambda 1 q tilde dot plus lambda 2 q tilde. This will be m of q inverse tau. So the control input, actually, now we find out the control input so that the system will follow this aerodynamics. So I'm simply writing it as tau c. That's all we are doing it. Tau c would be simply nothing but, if I take this m of q to this other side, you will get m of q multiplied by q decide double dot plus lambda 1 q tilde dot plus lambda 2 q tilde plus n of q dot. This will be a control input. Tau c. That's all. This one. This would be the correct answer actually.
Okay, sir.
Yeah.
Sir, can you go to week 2 question?
Week 2.
Week
Okay.
assignment week 2. In that there is one question 13.
Okay. Week 2.
In 13.
Let me check.
Which is about
Week 2 question 13. Okay. Yes.
if you read that statement here,
Yeah.
it's clearly given it's a clockwise rotation.
Okay. Yes.
Okay, but now if you go to week 1, 18th question,
Week
there
1, 18th. Week 1,
18th question.
18th question. Okay. Okay.
Here clockwise or anti-clockwise is not mentioned.
It says it's about positive y-axis. Yeah, the rotation matrix 30 degrees corresponding to 30-degree rotation about positive y-axis. Okay, understood. Yes.
But maybe a clockwise or anti-clockwise should also be mentioned. I'm not sure. That's why I'm asking. Is the question
Yeah,
complete?
that is true. That is correct actually. So it can be clockwise or counterclockwise or about the positive. Yeah, but the data is insufficient. Yes. So should I cancel that question?
It's up to you. We have anyhow come to the end of the session. Almost
yeah,
one question that make a difference.
Week 1, I don't know if no one actually wrote that question as wrong.
No,
Then probably
it did not occur
everyone assumed it
for
to
us
be.
at that time. No, it did
Yeah.
not occur for us at that time. Only after attending your lectures, started slowly grasping the subject. Then for the
Okay.
final exam preparation, and I'm reviewing this, then I ended up on this.
Okay, week 1, question 18. Yes. So if you have gotten this wrong, maybe I can cancel that question. So that won't be
No,
like.
see, it is the best of 6. I think I don't
Really?
require much.
Okay.
Anyways,
Okay.
I leave it.
Okay. Yeah.
Sir, assignment
Yeah.
7, 13 questions, sir.
Assignment 7:30. Okay.
The word asymptotically, I have a doubt, sir.
Okay.
Sir, can you show the question, sir?
Question 13.
Asymptotically something will come.
Assignment 7 asymptotically. Let me check.
14.
Yes, 14.
Uh,
Question 14. Yes, asymptotically or exponentially stable means.
Then I gave the answer B, sir.
Okay, when time
I
tends
have
to
it.
infinity.
The
Okay.
answer is 0. The answer is 0. Sir, asymptotically means, I think my opinion is, it will
Yeah.
not reach 0, sir. Is it right? Then
It will not.
definitely there
It
will be an error, na, sir. There will be error.
there
There
will
will
be
be
error, but
definitely.
no, it'll be
Then,
asymptotic to this time axis. If there is a time axis in
okay,
it,
sir. When
then
time tends to infinity, there will be
yeah,
some error. That is my opinion.
there will be error. Error
Theoretically,
only tend to 0. Error does not become 0.
if you have not given error 10 to bounded, I might have checked the tends to 0. When you have given, this is my
Yeah.
opinion, only the opinion, my opinion. See, because you have given that there is a bound to be error means definitely there will be some error that we know practically.
Yes.
Is it right? So that's why I took the B. And here the answer is the tracking error tends to 0. That is the theoretical
Yes.
one, sir. So
Yes, error tends to
why
0
you
actually.
have
So
given that option, that I am asking here.
which option?
Infinity, either you might have given tends to infinity or tends to 0. Then we might not be getting the doubt here. But when the option is like striking errors tends to be bounded, that means definitely there will be error, because we are not touching that particular x-axis, na sir. When
Hmm.
we draw the curve asymptotically, that curve will be, we are drawing parallel to the x-axis.
X-axis,
Is it
yes.
true, sir? So then we
No,
are saying that
no, no,
some
no.
error
That's
will be there, na?
parallel to x-axis means it can be, it can be parallel
Uh,
like this. But asymptotically,
Exponentially, it will be rising or it will be decreasing. One, definitely
yeah.
it will be horizontal.
So
It is,
this is again after a while it
this is
actually
my
becomes
opinion, sir.
parallel.
This
Yeah,
is my opinion only, sir.
yeah. But bounded actually means it could be bounded anywhere. So like if this point is something
Error, this is
probably,
error, sir. Error is
yeah,
bounded.
error is bounded. If this could be probably around 10 units, this could be within a bound that is close to this 10 units. But asymptotic means it basically 10 to 0. See, it more or less it runs it's just not parallel, it's also more or less coincident with this time axis actually.
Can you show any graph, sir? In your textbook or anywhere, can you show that graph? I don't know. I am not mechanical
Textbook,
student. I
yeah,
have
yeah,
not seen any graph. You can show the graph.
okay, I'm simply drawing it actually. If you want to have a textbook proof, I can probably maybe get back to you, maybe
No,
probably
no, no. You
later.
can draw. You can draw, sir. Now you can draw. Then
Is
later I will check.
I think my screen is not responding, I suppose. Can
This is
you?
notepad now, sir. This is notepad now.
Yeah, but it's
The
not
shared
responding,
one
I
is not.
suppose.
Okay, sir.
Yeah,
See, I told you just my opinion, sir. Because you have
yeah,
given the bounded error, I overlooking, overthinking, we have given that particular
yeah,
option.
but it's a good point actually. I probably may need to ask with consult with professor, and I also need to ask his opinion as well, whether that question makes any sense or not, because you have raised a valid point. So I'm not sure why my screen is actually not
Okay, now, sir. You understood my
responding.
point, now, sir. You understood
Yeah,
my point.
I
Okay.
I got your point. So I'll consult with professor and see if he can, uh, you know, uh, cancel the question or not. Because if it creates some unnecessary doubts because of the question is not properly framed, we can actually, we can probably discard that question. So what I mean by asymptotically stable means if this is the time axis and if this is the error axis, asymptotic stability means as time tend to infinity, the error basically it tends to 0. It goes like this. There is not much feasible. Uh, yeah, there is not much feasible gap between this x-axis or the time axis and the error. But if
We
there, if
will not touch the horizontal axis where I feel.
yeah, we won't touch it, but it's very close. It goes very
Yes, sir.
close.
Yes, sir.
Yeah, because it becomes
Yes, sir. Yes,
infinitely
sir.
small, but it won't be exactly 0. But bounded basically means it goes like this, it goes flat like this, but there is actually a
That
finite.
is okay. Okay.
Sir,
So you're thinking that NF amplitude will be there, that you are saying that bounded error,
Bounded,
sir.
actually, yeah. Yeah.
Okay.
asymptotic, I feel if you are
Yeah.
having an error, say 1, you go
Hmm.
2 steps forward, it will be 0.9. You go again 2 steps forward, it will be 0.8. Again, you go 2 steps forward, it will be 0.7.
That
Like
is
that, it
linear,
keeps
right? We cannot
on
call that
decreasing.
to be, that is more or less like a linear behavior. We cannot call it to be an asymptotic, an
No, I'm not
asymptotic state.
telling linear. The
Yeah.
thing is, it keeps on decreasing,
Yeah.
but will never go to 0.
It will never go to 0. That's why, because
Yeah,
this
but
e raised to
you
minus,
again take some more steps, go forward, it will again reduce. You again take some
exactly.
steps forward, it will again reduce.
Yes.
That is what my
Because
understanding.
if you have this term like, if you have a term something like e raised to minus t or e raised to minus 2t or something, theoretically this term can only get so small. It can never be exactly 0. But as time goes to infinity, this term what will happen to this term? As time goes to infinite, this term
Tends
will
to 0.
tend to 0
Tends
actually.
to
Yeah.
0. Yes, sir.
But yeah.
Sir, if it is only exponential, we might have kept the tends to 0. But when you have added asymptotically, then it has given a confusion to us. If it is only exponential, we might have written the extends.
Okay,
that
so
is my
we'll
opinion.
okay, that is
Yes, sir.
that's a valid point. So we'll look into it and we'll update that. If the question is confusing, we'll withdraw that question.
So there is one more question. Week 4, question number 12.
1 second. Which question was this? Week 7, question 14, right?
14, sir. 1-4.
Yeah, week 7, question 14. Okay. Sure. We'll also look into this. Okay, so which is the other question?
That is only sir, doubt.
He was asking some other question. It was
Okay.
week 4, right? Week
No,
4.
what? No, current one. Okay, week 4, question
Yeah.
number 13.
Week 4, question 13.
12, sir. Sorry, 12. Question 12.
Okay. Week 4, question 12.
If R is a rotation matrix and it is time independent, S plus S transpose equal to 0, where S equal to R dot transpose R transpose. Sir.
Okay. Yeah.
But that notes shows that S equal to R dot multiplied by R transpose. Sir. So will R dot transpose also will be right? That
if the rotation matrix is R, then S plus S transpose is 0, where S is
R dot transpose, no. If you see
R
the
dot transpose R transpose.
in the forum, I have send an email.
Okay. Yeah.
I have pasted the pictures there.
Okay. So it is not correct, right? I think S is not R dot transpose R transpose. It is different, I think.
Yeah. If you take
S,
the whole transpose, the order will be reversed. That's what my thought process is. So that should be false.
that should be false. Okay. This is week 4, right?
Right. Week 4, question 12.
Week 4, question 12. I think this was addressed. No. I think you have raised this long before, right? Not recently.
Long before. No, this not recently. Long before, but there was no reply for that. That's why I'm asking.
Okay.
Because
Okay.
these are not written. I felt like so far I've written few exams. Most of these questions, at least 60 to 70% come in the end examination, final
Okay.
examination, and they go same answers.
Okay. Yeah.
Sir, assignment 6, sir, question number.
Well, 1 minute. There again, question number 4 also, no, not question number 3 also needs to be corrected.
Question number 3.
Sorry, ma'am. Yeah.
Question number 3. Okay. Question number 3. What is the problem?
For non-square, the independent columns.
Yeah.
I felt like answer is B, but here it is taken answer as A.
Okay. For a non-square matrix with linearly independent columns. So linearly independent columns means it'll have.
If you open the email, I have posted the picture of that.
Okay, so this is again week 4, question 3, right?
Right, week 4, question 3.
Okay. Week 4, question 3. So let me check this answer.
Yeah, no problem. If you
So
open the bottom, you'll see a picture of that.
independent columns, Moore Penrose inverse, right inverse. Linearly independent columns, what does that mean? If the system becomes
Linearly independent means columns will be less than rows.
okay, so more number of rows means more equations than unknowns, right? Than unknowns.
Okay.
So it could be an overdetermined system, right?
Right, overdetermined.
In overdetermined system. So overdetermined system may not even have an exact solution. So for that, what do? We find this minimal norm. No, not the minimal norm. We do this least square optimization. So for that, we do this left inverse, I suppose. Left pseudo inverse. So that will be J.
What sir was mentioning is we
Transpose
multiply
J,
that
the whole
J
inverse.
transpose in such a manner that the J transpose will always be on the minimum side.
Yeah, so you are saying that the option is B, right?
No, option is, yeah, that's what the lecture notes, you see it.
Yeah, exactly. Option is B, but the question is wrong actually. The Moore Penrose, it's not it's not the left, the right, it's not the right inverse that is asked in the question. It should be left inverse.
Okay.
Yeah.
There is a
Yeah,
confusion
so
there.
that is,
So for independent columns, it should be left inverse, and for independent rows, it will be right inverse. Is that the way?
you are correct actually. But the question is actually long. It says linearly independent rows, but it also asks you to find out the right inverse. So both are contradicting. So yeah, that question itself is indeed wrong. Question itself is contradicting. For
I
linearly
am
independent,
not sure
yeah.
why it
So
is contradicting, sir.
yeah, so thank you very much for pointing that out. So yeah, we'll take a note of that. Week 4, that also need to be cancelled actually. Yes, and I think
Question
for
3.
whatever you have said earlier, that which question was that? Question 12, right?
12, right? 12.
Question 12. That should be. I'm not sure. I think S should be R dot
R transpose.
R dot R transpose, right? That should be
Right.
S.
Yes, sir.
So R dot R transpose, not R dot transpose R transpose. So that should also be false. Yes.
Right.
So yeah, that is also a mistake actually. Yes, yes. I agree with that. Yes, correct.
Sir,
Okay.
assignment
Yes.
6, question number 5, sir.
Okay.
Assignment 6.
Assignment 6. Assignment 6. Question number 5. Okay. Yes.
Sir, here we calculated the velocity at 3 seconds, 5 seconds, where the instants are the middle instants. And t is equal to
Okay.
7 is the final position, sir.
Okay.
I think s-
So what? So actually, what is the problem? The time equal to 7
that means,
seconds. The duration is for
uh,
7 seconds, right?
yes, sir, yes, sir. That means where when we reach the final position, what is the velocity, sir? Is it 0 or how it goes on? Where we thought that initial velocity and final velocity are the 0, no, sir?
Yes.
Shall we read now?
It actually instantaneously shoots up at that instant itself. Yeah. So
Sir,
that
sir,
is also, yeah.
sir, one more, sir. Read the question number 2. The initial and final position of a joint variable theta are given as theta a 30 m, theta f
Yes.
100 m.
Yes.
The total time for the joint to reach from initial position to final position is 10 seconds. Okay, it is my mistake, sir. Now I have a doubt, sir. When it reaches the 10 seconds, is it the velocity is 0 or not?
It's
Maybe here my answer is maybe wrong here. Here at t equal to 3, the 7, and at 5 also the 7. We calculated with the formula. And then at t is equal to 7, I kept to the 0. Maybe wrong. But when finally at 10
actually the
seconds,
thing
what
is
will be the
it's a
velocity?
straight line. It's a straight line trajectory, right? So the velocity should be constant everywhere, right? Because if you take a derivative of a straight line, it will be constant. Derivative of a straight line with a slope, velocity would be a constant actually. So velocity at time 3, 5, 6, 5, and 7, all these things would be still 7, I think. Answer would still be 7.
at 10 seconds, sir. Even at 10 seconds, it is.
Even at 10 seconds also, it should be 7 because, that is a problem with these sort of trajectories actually. Straight line, cubic and all those things, it'll
Then
have
at
this
t is
sudden.
equal to 0, sir. Then at t is equal to 0.
Yeah, because
When
if
it
you
is
take
straight line, how it gets the velocity?
no,
Like
the thing
7
is,
meters
yeah, the
per
velocity
second.
profile would look something like this. The velocity profile would look something like this. Maybe at time, if this is 0 and if this is 10 seconds, the velocity profile would look something like this. At time t equal to 0, it'll jump up suddenly like this. It'll be flat all the way. Then suddenly it'll drop down like this. This is how the velocity profile would look like. It's like a triangle. Sorry, like a rectangle with a constant velocity. So if this is
Then position is
velocity,
straight line, sir. Then position is straight line.
position would be something like this. Position would be something like this.
That is the straight line interpolation. Is it the straight line interpolation?
Yes, it's the straight line interpolation. The question actually says, right, use straight line interpolation. If you take a look at this question number 2, that is the main question, and the following are all
Yes, sir.
fill in the blanks, the sub questions of that. So it is straight line interpolation, and yeah, it is indeed straight line interpolation, and velocities would be constant at time t equal to 3 seconds, time t equal to 5 seconds, and t equal to 7 seconds actually. And if you want to work that equation out, it's a straight line interpolation. Simply that will become, I don't know, I'm not sure about this formula, theta minus theta initial. So that'll be 30, and the other would be 100 minus 30.
100 minus 30, 70 divided by 10. So it is 7. The slope is 7, sir.
70, is
70
it 10?
by 10 seconds. 10 seconds.
Yeah, 10 multiplied by, what is the final time?
10 seconds. Sir.
Okay. Yeah.
Okay, sir. I got the answer. It is my mistake where I thought that at 10th second also the velocity going to 0, but you are saying that it will maintain the same velocity.
Yes.
So then the
it'll
7th
be
question, sir.
7 minus
7th question.
Yeah, TF. Yeah,
Then I
seventh
kept
question.
the statements 3, 4, 5 are the correct, but here the answer is 1, 3, 5 are correct.
Okay,
So
straight line interpolation. Okay, we'll go through that. Question 7 is straight line interpolation has constant velocity throughout from start of the interpolation to the end of the interpolation. So, yeah, that is true. One is true. And straight line interpolation has constant non-zero acceleration throughout, but with an instantaneous infinite acceleration at the beginning and at the end of the path segment. As a constant non-zero acceleration throughout, that is false, right? Because acceleration will be 0. Because if velocity is constant, its derivative acceleration would be 0 throughout, but it will have some instantaneous, infinite jerk kind of a thing at the start and at the end. So that is true, but non-zero acceleration is actually false. Acceleration is going to be 0. That is false. And 3 would be straight line interpolation has 0 acceleration throughout, but with an instantaneous infinite acceleration at the beginning and at the end of the path segment. That is true. 4th is a quadratic polynomial can satisfy the position and velocity constraints at the start and at the end point of the path segments. Satisfy the position, that is a quadratic polynomial. No, that is not true. A quintic polynomial can satisfy the
that
position
is true,
velocity.
Sir. That is true.
That is true. Yeah. So 1, 3, 5 are the correct answers. Yes. But if I need to explain,
4. What is 4?
4
what
is
4, sir?
a quadratic
4.
polynomial. For example, if you write this theta, if you express this theta as, can you see my board? I think it's not responsive in a lot of lot of time. Let me try and connect it once again. Okay. 1 second. Yes. Yeah, so a quadratic polynomial would something like this. Theta is a0 plus a1t plus a2t square. So like you only have three unknowns over here. So you can only have three equations or three boundary conditions. So position. So you can have one equation for initial position. You can have one condition for final position. Maybe you can have one equation constraint for initial velocity. You can only have three equations. You cannot have more than that. So you cannot have all the initial and final positions and initial and final velocities as well, because that would require four equations or four boundary conditions, right? That is why we use this cubic polynomial theta as a0 plus a1t plus a2t square plus a3 t cubed. So we will have four unknowns so that we can use four equations to solve these four unknowns. And the four equations are the boundary conditions on positions, initial and final position and initial and final velocities. So like we'll have four, but in the quadratic, we can only have three equations. So that is why that point that says, a quadratic polynomial that can satisfy position and velocity constraints at the start and the end point of the path segment, that is false. It cannot, because it can only satisfy three constraints of the maximum.
Okay, sir.
Yeah.
Sir, I need to take leave. Have a nice day. Bye.
Thank you. You too as well. Please.
Is there any more live session? Is it the last one, sir?
No, we may have one more at 2. I think on Tuesday. I think just to summarize everything.
Next Tuesday, sir. Next Tuesday.
No, the coming Tuesday. Yeah, just to summarize everything.
Okay, sir.
All the topics. In
Can
brief.
we expect from the material the questions, sir?
The question. Which question?
Material examination questions. From the material and assignment questions, can we expect the similar questions?
You can
The
expect more or
examination?
less similar questions. From the material as well as from the live sessions, you can expect similar questions.
Thank you, sir.
More or less
Thank you,
similar.
sir.
But if you have any doubts, please clarify. Just like you use the session for clarification, I
Okay, sir.
appreciate that. Thank you.
Okay, so next on. Thank you, sir. Thank you, sir.
Yeah.